Hi and welcome. I'm trying to learn Biographyology. Today, Chien, Shiung, Wu, and after we've done it, we're gonna do shoulder impingement training. And if you participate in the shoulder impingement training, then it's better on risk. And we did this article a couple of times in particle physics, so it's a completely new thing. Chien Shiung Wu's broken mirror. It was investigation of a weak force by Chinese-American physicist Chien Shiung Wu that provided one of the most profound demonstrations of the importance of broken symmetries in particle interactions. We're getting now a bit of explanation. One of the most basic symmetries we know of is mirror symmetry. And in particle symmetry, this goes by the name of partisymmetry, a principle that says particle processes, collisions and decays, what particles can do, should happen in the same way if all the positions and orientations of the particles involved are flipped in the mirror. Basically, if the setup is mirrored to the other side, all should happen the same again. I understand it that way. If you're having a bunch of atoms, particles, whatever, in one room, and exact the same setup of atoms and particles in another room, all the atoms are at the same position, all is the same orientated, it should happen all the same as in the other room. The way they collide together or decaying, whatever these atoms are doing, it should happen exactly the same as in the other room, because it's the same room, basically. It's mirror. A perfect mirror. In 1956, theorists Li and Yang showed that partisymmetry, so that both is exactly the same basically, was valid for interactions involving electromagnetism and strong nuclear force. But they found no evidence for it holding in interactions involving the weak nuclear force. I don't get it all what it is, but that means it is true it happens the same regarding to the strong nuclear force that is doing something. I didn't really get it. Whatever, they are doing some things because there's a strong nuclear force having effect on them, and that happens the same in both rooms. And also electromagnetism works the same. I don't know what it is. Let's just say it's a magnet. A magnet has exactly the same force on all the objects in both rooms, but the weak nuclear force is not the same. And that is something how inside of these atoms the neutrons and protons are interacting or decaying or whatever, something like that. And that happens not the same. So they showed, or here was these two, Li and Yang theorized about it and pronounced that will not happen the same. Okay, they showed it, whatever. And they showed it now, and they showed, I don't know what showed means, it happens the same. In these two things, both doing the same, but not the weak interactions. Even though it is completely the same setup, what they're doing with the decaying of the neutrons and protons or whatever, happens differently than in the other one. I just realized something, but this is particle physics. So, born in China in 1912, so we're here for Chien Shiung Wu. She was born in China in 1912. Chien Shiung Wu moved to the US to do a PhD in 1936. I don't know what a PhD is, what these three letters mean, but that is something which people who want to become academic have to do or doing. So to proving this paper, whatever it is, but it's a long paper, that they actually know what they want to do as a business, as a profession. So, and she went to the US to do a PhD in 1936. She never saw her parents again. So we're going to talk about the Second World War. She never saw her parents again. The Second World War and the accession of the communists to power in China meant Wu didn't return to her birth country until 1937, and then only as a tourist. So she was born in China in 1912, when 1936, before the Second World War and also before the Pacific War broke out, to the United States to study there and do a PhD in particle physics or something. But when the Second World War broke out, and in China the Communist Party got the party which is leading the country, and she did not went back to China as a tourist in 1937, but she did not settle back to China. Throwing herself into her work, the University of California, it's now in the 1930s, 40s, 50s, 60s, must as well be, throwing herself into her work, the University of California, Berkeley, home of the pioneering particle accelerator, she became an authority on beta decay and also worked on the wartime Manhattan Project to build the first nuclear bomb. Okay, let's say in the 30s, after she had made a PhD around 1936 in the 30s, in the 40s, she worked now at the University of California. Is the university named Berkeley, or is it in Berkeley? We're going to say just University of California. I don't know what the Berkeley means. And this University of California has a particle accelerator. I don't know exactly what it is, but basically having a machine with which we can accelerate particles. I have a thing, so what is the thing called? There's a thing which can blow air, hot air, and basically like that, and they're just making faster and faster particles, atoms, and then they can let them collide, and then they can watch what happens, how they collide. Whatever, they had such a particle accelerator, and she became in a 40 or important, I don't know what now really 40 means in this context, but she became a very important person in beta decay, and that is a neutron decaying into a proton, or a proton becoming into a neutron. The universe is made up out of atoms, and these atoms on the inside have on the nucleus of protons and neutrons, and these neutrons inside of them have different things, whatever, but that's not the point. These neutrons inside of them can become just protons and become neutrons and whatever, and that is beta decay. That's some sort of decay, what we're just doing. And she became an important person at it. And she worked also on the Manhattan Project, that the first nuclear bomb. In 1944, I think they started in the United States to work on building a bomb, not based on dynamite or something, but on atoms, which, what are they actually doing? Whatever, they're atoms, and they're then suddenly releasing all the built-up energy. And instead of doing it slowly, like in a nuclear reactor, and getting the energy to make electricity out of it very slowly, we're doing that very fast, not over a course of days or weeks or whatever, how fast it works in a nuclear power plant. We're doing that in a split second, and that whole thing doesn't give slowly off its energy, because we have it all accumulated together by accelerating. I don't really know how it works. And the idea was not to build it together. We are having, and they had now uranium and different other things, and we could enrich with more and more, and now there was more and more energy in it, and instead of releasing it now slowly and making electricity, we had the idea, what if we're basically making less, making a lot of this uranium, and then releasing this energy immediately in 1 second, and that was one an atom bomb, because now it's not slowly radiating, generating heat or something like that, and generating electricity. I don't know actually how a nuclear power plant works. Whatever, instead of releasing it slowly, how about we letting that release very fast, in a split second, and now it comes out with one big boom, and that is a big boom, and that is an atom bomb. So it explodes suddenly and makes a gigantic fireball, multiple miles or kilometers big fireball. And there she did it, and so we're talking about this thing, 1200 nuclear bombs. And these nuclear bombs were actually used in Hiroshima and Nagasaki in Japan. Now, she was from China. To be confused, she was from China, and she was in the United States and working on the Manhattan Project, and the atom bombs were in front of the United States on Japan. Japan was an enemy of China and of the United States during the Second World War. She was from China, and the atom bombs were built against Japan. Japan had attacked China very brutally. So she and him were the nuclear bomb building. In 1956, Wu designed and built an experiment at the US National Bureau of Standards in Maryland to test Li and Young's idea by looking at the directions in which cooled cobalt-60 atoms trapped in the magnetic field emitted beta decay products. So when in 1956, the same year when these other two people, Song-Dao Li and Yang Chen-Ning, thought about that, hey, the weak nuclear force does not react the same as the strong nuclear force of the electromagnetism in the other room the same way. She took now cobalt-16, so an element, and she took it with 60 isotopes. I don't know how to works. She had cooled it down. She said, whatever. She had it in the refrigerator. I'm going to save it just like that. She had this element and cobalt-60, and she had that now cooled down, that whole thing. And then she put it between magnets or between electromagnetism. She trapped it in the magnetic field. And then she was looking how now inside of these cobalt-60 atoms, all with the atom in the middle, with all these cobalt-60 atoms. So she had the cobalt-16 in the middle, and the nucleus of these protons and neutrons, and how we know decaying beta decay, how these neutrons inside of these cobalt-60 were turning into protons and giving off an electron, and we learn how a proton becomes a neutron giving off an electron, I think also. And how it was happening in what directions. As he said, I don't understand the word directions in the sense. Does it mean, does it come to the right or to the left? Or does it mean, does it happen the neutron into the proton or the proton into the neutron? What's meant with directions? Whatever. She was looking how now inside of these cobalt-60, these atoms, these protons, inside of the nucleus were turning into neutrons, or neutrons into protons, giving off an electron. And actually now, sure enough, she found an asymmetry. Party symmetry was broken by the weak interactions. That means it was not happening the same. And she could prove, yes, actually, I have cobalt-60. I don't know really what she was doing, but I just assume it now. She had cobalt-60 and set it up the same way correctly, whatever, and it was not happening all the time the same way. And that proved it is exactly the same setup, but it's not decaying in the same way. Sometimes it becomes more protons, sometimes more neutrons, whatever. I don't know, it's not written in detail here. So actually, the weak nuclear force does not work the same, even if everything is set up the same. This had huge ramifications for explaining how a weak force worked and provided a first view on other broken symmetries within what became the standard model, including the CP symmetry violation that might explain matter dominance over antimatter in the universe. There's 2/3 matter and 1/3 antimatter. I don't understand what it is, but I think no one knows what it is. That's the whole point of it. Whatever. I don't have time to go through it again, and then also. So we're going to do the rest in the next one. Is that what? That means if you were here for Biographyology for Chien Shiung, you can go directly to the next part of Biographyology where we will do the continuation. We will do now the, I have no idea, the short impingement training. If you stand participate in the short impingement training, means that the hour is go to stable stance and do short circles. Run back, up, and front, and another round, back, up, front, down, and out, front, up, back, down. And now long arms, strong fists, and go as far back as you can with the shoulders. High up, and front, and down, back, up, front, down, and then backwards. Up, back, down, front, up, back, and down. And now go on the knees, hinge forward with a straight back, let the arms hang and pinch the scapulars together with it. Make fists, lift the arms up and still pinch the scapulars together. Lift the arms down, also the shoulders, and then horizontal, pinch the scapulars together with it. Make fists, lift the arms up and still pinch the scapulars together. Lift the arms down, lift the shoulders, and now down, hinge forward, this time with a round back, let the arms hang, make fists, turn the arms to the inside, lift the arms up, together, straighten up, bring the shoulders down, and together. So the arms up, and together, shoulders down, and together. And again, into the knees, hinge forward with a round back, with the arms hang, make fists, turn the arms to the inside, arms high up and together, straighten up, shoulders down and together. So arms high up, together, shoulders down and together. Release, and now lift the arms up. If this or any other exercise causes pain, then don't do it. And again up. And down. Arms to the sides, and the front, and back, and the front, back, front and the other side. And now, we will lift our long arms, strong fists, go the shoulders down and together, arms to the inside. Turn the arms to the inside, shoulders down, together. Arms to the outside, shoulders down, together. Arms to the inside, shoulders down, together. Arms to the outside, shoulders down, together. Release. Arms up, a bit in front with the fists, the arms. The arms in front, shoulders down, hands together. Arms back, shoulders up, and in front. And arms in front, shoulders down, and together. Arms back, shoulders up, and in front. And release. Now shrug, the arms up, shrug the shoulders up, and release it down. Again, the arms up, shoulders up, and go down. Last time, arms up, shoulders up, and down. And now, with some leg that you can use a sock or whatever, have it long on the outside, let it fall down, and try to catch it again. And on the other side. Now stretching. One arm in front, shoulders back and down. Pull the arm in, left fingers, try to relax the arm. Go with back of the shoulder, turn the palm up to the sky. And the other arm in front, shoulder back, down. Pull the arm in, left fingers, try to relax the arm. Turn the palm up to the sky. Back of the shoulder, touch relax the arm. And that was the shoulder impingement training. I thank you very much, and until next time.